Okay, this is Math 131, section 2.3, and we're going to talk about how we represent sets using what we call Venn diagrams. So Venn diagrams usually look like this. There's a box which represents our universal set. We call that U, and that would be everything that's in our set. Or anything that's in our universe. Okay, so if we're talking about the natural numbers, our U would be 1, 2, 3, 4, 5, 6, 7, 8, etc. Okay, so that box represents our universal set. Okay, rectangle for universal set U. The items inside the rectangle, now you can take parts of that. So we could take a subset of U, okay, which we might use as maybe set A, okay, and then we could use a circle for that, okay. So for the things that we're using parts of our universe, we're going to use circles like A here, okay. So this means A is part of the universal set, it's a subset of the universal set. So maybe U is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc., and then A is just 1, 2, 3, 4. Okay, if two sets don't have anything in common, we say those are disjoint sets. Okay, so disjoint sets have no elements in common. Okay, so when we take the intersection of those, we see where we're in both sets. That will be the empty set. Okay, so we can say that for this case, A intersect B, remember that's the intersection is upside down U, is equal to, well, we can just say empty set, right? So we can just put those braces with nothing in it, okay? So there's no elements in common since there's no overlap. We say those two sets are disjoint, and then we were drawing the Venn diagram where they don't cross at all. When we talk about proper subsets, like here we'll say A is a proper subset of B, okay? Or A that sideways U, B without the equal to. That means circle A is completely inside circle B. And we can see that, A is completely in B. So let's say U is our natural numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, etc. Let's say B is 1, 2, 3, 4, 5. Then A, maybe A could be 1, 2, 3, 4. So it's part of B, but it's not all of B. Okay, but everything that's in A is in B. Okay, and we would draw it like that using our Venn diagram. If our sets are equal or they have exactly the same elements, we write that as A equals B, right? We would just draw both sets as the same circle. So you would see kind of, we're just labeling the same circle. You see it's one circle, but they're both A and B. When sets have some elements in common, we're going to write it like this. Okay, we'll have A and B and they're crossing over. So this region in between is where A and B overlap, or where A is intersecting B. So we would put the elements that are in both in that. So let's say, well, we'll look at a different example on the next slide. And this is the most general form of how we would describe two sets inside a universal set. That we would show them overlapping, and maybe we could say, well, maybe there's nothing in this overlap. Maybe they don't overlap really. Okay, so when we draw it that way, what we have are four potential regions, and we're using Roman numerals here. But region 1 is going to be where we're in A but not in B. Okay, region 2 is where we're in both A and B at the same time, and then region 3 would be where we're just in B. Okay, and then the fourth region is where we're in our universal set, but we're not in A or B. Okay, we're not in either one. Okay. Okay, so let's look at this example. Let's say A is 1, 2, 3, and B is 3, 4, 5, and our universal set is 1, 2, 3, 4, 5, 6, 7, 8, all the natural numbers, right? So Roman numeral 1 would have 1 and 2 in it. Okay. Roman numeral 3 would have 4 and 5 in it. Okay. And then this Roman numeral 2 would have 3 in it. So 3 is, you can see, 1, 2, and 3 is in set A. Okay. And then 3, 4, and 5 is in set B, that circle, and then 3 is in both sets. Okay, and then we could put the rest of the numbers out here, like 6, 7, 8, 9, etc. So all the other numbers would go out here. So that's an example of how we would place all those elements, in the different regions using a Venn diagram. Okay, we say A is a subset of B. We could have two possibilities. We could have A be completely inside B. Okay, so like this is our A on the inside, and this is our B on the outside. Or we could have them just be the same set, right? And that means A is equal to B, okay? So So we can say, okay, here's where A and B are equal, and that would be when A equals B. And then here's where A is inside B, and that would be A would be a proper subset of B. So that's how we would define this. A is a subset of B. But we would say that region 1 would be empty. In other words, there's nothing in A that's not in B, right? So this we would not have anything in region 1. Okay. And then if we had the opposite, where B was a subset of A, okay, so let's put that down here. Now we would have B inside of A completely, or we'd have them be the same set. Okay. But in either case, there's not going to be anything in region 3 because everything that's in B is in A. Remember, when B is a subset of A, that means everything that's in B is in A. So there isn't anything in B that's not in A. So this region 3 would be empty if B was a subset of A. Okay, when set A equals set B, remember it's just the circle, and they're both the same, right? They're both, A is that circle and B is that circle. So we would also say here that there's nothing in region 1 because there's nothing in A that's not in B, and there's nothing in region 3 because there's nothing in B that's not in A. So we wouldn't have anything here, we wouldn't have anything here. We can still use this diagram, we would just not put anything here or here, okay? But just keep in mind that that's what we're saying is that those sets are the same. Okay, so just to recap, when sets A and B have elements in common, those are in region 2. Okay, so that's where we'd have the region elements in common. Elements that belong to set A but not to set B would be in region 1. Okay, so that'd be here. Okay, and then elements that belong to set B but not to set A, that would be in region 3. Okay. And then anything that's in neither A nor B would be region 4. So anything outside the circles is what's in the universal set, but not in A or in B. Okay, so let's say our universal set is the natural numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. And then set A is 1, 2, 3. Then A complement, sometimes we say A not, is everything that's not A that's in our universal set. So we would have not use 1, 2, 3, but we use 4, 5, 6, 7. So everything that's not in A complement, and we use A with a little dash or the little, what do we call that? Single quote, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc. Okay, so here's an example. Set U is A, B, C, D, E, F, G, lowercase, and set A is A, C, E, so it's part of that universal set. Okay, so we want to find A complement and illustrate the relationship among sets U, A, and A complement in the Venn diagram. Okay. So here's our universal set is that rectangle. Okay. A is going to be the circle, and we just have A, C, and E in there. Okay, and then the other ones are going to go outside that in the universal set. So this is where A complement is outside the circle, but inside the rectangle. So B, D, F, and G are the other ones that would be A complement. So there's A prime. We sometimes say A prime or A complement, B, D, F, G. Okay. Okay, the intersection of two sets is A that's upside down U, B. Okay, so we see that symbol. That means we're taking the set containing all of the elements that are common to both set A and set B. Okay, and sometimes we use the word "and" for that, and that's region 2 in our standard Venn diagram. So that would be this region where we're in both sets, both of those circles at the same time. Okay, that's the intersection. So let's say our universal set is the numbers 1 to 10, and then A is 1, 2, 3, 8, and then B is 1, 3, 6, 7, 8. And then C is just the empty set. So C is no elements. Okay, so we'll find A intersection B, A intersects C, A complement intersect B, and A intersect B complement. Now be careful with the parentheses here because when you see parentheses you have to do inside the parentheses first and then take the complement. So we'll talk about that next when we get to that example. Okay, so A is 1, 2, 3, 8, and B is 1, 3, 6, 7, 8, and we're looking for the intersection of those two sets, A and B. Okay, so we're just looking for which elements are in common. 1 is in both, 3 is in both, and 8 is in both. So that would be our A and B. Okay, so we could just say this. A intersect B equals, using set notation, 1, 3, 8. Okay. Okay, part B, we're looking at A intersects C, or A and C. So A is 1, 2, 3, 8, and C is the empty set. Now, C doesn't have any elements, so there are no elements in common to both sets A and C. So we can say here that A intersects C, or A and C, is just the empty set, because there are no elements that are in both. Okay, for part C of this example, we're looking at A complement intersect B, or A complement and B. So the first thing we should do is always determine that A complement. So since A is 1, 2, 3, 8, and our universe is just 1 to 10, we're going to pick all the numbers from 1 to 10 that are not in A. So we're going to pick 4, 5, 6, 7, 9, and 10. That would be A complement. Now we take that A complement and intersect it with B. So we see which elements these two sets have in common. A complement 4, 5, 6, 7, 9, 10, and B 1, 3, 6, 7, 8. We can see that 6 is in both and 7 is in both, and that's it. Okay, so we would say A complement intersect B, or A complement and B would be 6 and 7 only. Okay, in our last part of this example, we're taking A and B complement. So we have to determine A and B first. Now we already did that in part A, right? So A and B is 1, 3, 8, okay, from part A. And then we're going to take the complement of that. So we're going to look at everything that's not 1, 3, 8 in our universal set. Okay, so that would be 2, 4, 5, 6, 7, 9, and 10. All of these that, not 1, not 3, not 8, but everything else. 2, 4, 5, 6, 7, 9, and 10 would be A and B complement. So we do the parentheses first, then do the complement when you see parentheses there. Okay, let's talk about union of sets. We talk about the union of sets, A and B. We use the symbol A union B. Okay. It's the set containing all the elements that are members of set A or of set B, or of both sets. Okay. So what we're looking at in this case, for our standard Venn diagram, is this region 1, which is the ones that are just in A, region 2, which are the elements that are in A and B, and region 3, which are ones that are just in B. So it's going to be all three of these regions together would give us A or B. Okay. In other words, anything that's in either one of these sets, or in both, that would be the union. So let's say we're taking again, our universal set is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now our A is 1, 2, 4, 6, and our B is 1, 3, 6, 7, 9, and our C is the empty set as before. Now we're going to take A union B. Now remember, now we're just collecting everything. When you see that union, you're collecting everything. You're not looking for where they have elements in common. You're just looking for where you have any elements at all, okay, that are given. So if we're saying A union B, we're going to throw all these together. Okay, so A union B is 1, 2, 4, 6, union, 1, 3, 6, 7, 9. So throw all those together, and we get a 1. Now we have a 1 in each, we just count it once. Okay, and then there's a 2 here, so we'll include the 2. There's a 3 here, so we'll include the 3. There's a 4 here, so we'll include the 4. There's a 6 in both, so we'll include the 6. There's a 7 over here. There's a 9 over here. So you're just throwing everything together, right, and including everything. Think of like a labor union where it's all the workers are in the union. Everybody's included in the union. Okay, let's look at A union C. So A is 1, 2, 4, 6. C is empty set. Now we're just throwing everything together. We have 4 elements here. We have no elements here. So basically we're just going to carry over the A. Right? So we have a 1, we have a 2, we have a 4, and we have a 6, and we don't have anything over there, so we don't include anything else. So that A union C is just A. And that is because C is the empty set. It doesn't have any elements to contribute. Okay, for part C of this example, we're taking A complement or union B. So we have to find A complement first. So since A is 1, 2, 4, 6, A complement is going to be all the other numbers from 1 to 10. So 3, 5, 7, 8, 9, and 10. Okay, and then we're going to take that set, A complement, and throw it together with B, okay, the union. So we got a 1 from B, we've got a 3 from both sets, we got a 5 from A complement, we've got a 6 from B, we've got a 7 from both sets, we've got an 8 from A complement, we got a 9 from both sets, and then we've got a 10 from A complement. So everything thrown together gives us this. And again, the doubles we just count as 1. Okay, the last part of this example, we're going to take A union B complement. And just as before with the and, with the intersection, we have to do this parentheses first and then take the complement, okay? So the first thing we do is find A union B, which we already did. That gives us 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 6, 7, 9. Okay. And then the complement is going to be everything that's not these in our universal set. So we just have to look for the elements that from 1 to 10 that's not here. So that would be 5, 8, and 10. So that would be the complement of A union B. Okay, this can be confusing, but it's important that we understand the distinction here. When we talk about and, we're talking about intersection. Okay, and we have that upside down U. Okay, and this is called set builder notation, but we're using this notation, and this literally means this. Well, first we have our set braces, but we have this X bar, and this X bar means the set of all X such that. That literally means that. And saying here we're saying, okay, let's take a bunch of X's, and here's what we do with them. Make X be an element of A. Now that means is an element of that set A. And X has to be an element of B. So we're saying X has to be in both sets. Has to be in this set and this set. Okay. When we talk about the word or, we're talking about union. Okay. So that would be AUB. Okay. And then we use this similar notation. We have our braces, and then we have X bar, which means the set of all X such that. And this, when we use that set builder notation, we always use this notation. So X is an element of set A, or X is an element of set B. In other words, it can be in either one. It doesn't have to be in both. But it can be in both, okay, as we saw when we did the union before. If you remember earlier, we were talking about the cardinal number, and that means how many elements are in a set. So N of A is how many elements are in set A, cardinal number. Cardinal number B, or N of B, is how many elements are in set C. This would be the cardinal number, how many elements are in the intersection of those two sets. And then this would be how many elements are in the union of those two sets. Okay, so to find that first thing we're looking at, to find the number of elements in the union of two sets A and B, we add the number of elements in sets A and set B, and then subtract the number of elements common to both sets. So just to translate there, the number of elements in A union B is the number in A plus the number in B minus the number in A intersect B. Okay. So this is just a rewriting of that. Number of elements in A or B is number of elements in A plus number of elements in B minus number of elements in A and B. So to illustrate with an example, let's say A is 1, 2, 3, B is 3, 4, 5, 6, 7, and then A or B would be 1, 2, 3, 4, 5, 6, 7, and A and B would just be 3, right, the common element in both. Okay. So if we're looking at the number of elements in A or B, that's 7, right? So that'd be 7. And then the number in A is 3, the number in B is 5, and then we take away how many are in both, right? So how many elements are in A and B? So we 3 plus 5 minus 1 would give us that 7. Okay, so here's an example. Now this helps when you use a Venn diagram, to kind of illustrate what's going on. But we take a survey of visitors at the Grand Canyon. We show that 25 speak Spanish, 14 speak French, and 4 speak both Spanish and French. And we want to know how many speak Spanish or French. Now we say 25 speak Spanish. That doesn't mean they necessarily speak French or not. Okay, just say, do you speak Spanish? Yes. Okay. Do you speak French? Well, I didn't ask you that yet. Okay. So if we ask people how many people speak French, they may or may not speak Spanish. Okay, so we've got to use this information to kind of put everything together. We do know that 4 people speak Spanish and French. Okay, here's where we can use that cardinal number thing that we just looked at. Okay, this is the number that speak Spanish. This is the number that speak French. This is the number that speak Spanish and French. So what we can do is just add these two, 25 plus 14, and subtract the 4. So 25 plus 14 is 39, minus 4 is 35. Okay. Now we can also use a Venn diagram here. So what I can do is I can start by just drawing my universal Venn diagram where I have A is Spanish, B is French, and make them cross. And then I start by using this one, the number that speak French and Spanish, and I'm going to put that in region 2. So I would put a 4 here. That's how I would start to solve that. Okay, and then I would look at this set. Okay, set A is how many speak French. Well, we know that it's 25, right? But I already have 4 here in this circle. Remember, A is that full circle. So I would need another 21 outside of that A and B to get 25 total for A. You see that? See, I put the 4 there, and then I need 21 more to get 25. Okay. And then I do a similar thing for B. So for B, I have 14 that speak French, right? And I already have 4 here, so I would put 10 there. Okay. So I could put 10 here. Okay. And you see now for set B, I have 14, right? Because 10 plus 4 is 14. Okay. And then if we want to know the number that speak French or Spanish, okay, we can just add those numbers up. So we see 21 plus 4 is 25, plus 10 is 35. We don't add the 4 twice because that, it's 4 people, right? We're not going to add them 2 times, right? So we just add the people that speak just Spanish, the people that speak French and Spanish, and the people that speak just French. Okay, so we can use a Venn diagram to illustrate that as well. We don't have to use this formula necessarily to solve this. Okay, we talk about the difference of 2 sets, A and B. It's sort of like subtracting, and we use that subtracting symbol. Okay, but it's the set of elements that belong to set A but not to set B. Okay, so if you think of we're taking set A and we're taking away all the B stuff. So we're going to take region 2 away. So that would just be this kind of, it's like a moon shape, kind of that beige moon shape, would be A minus B. We're taking A and we're subtracting all the B stuff from there. Okay. And we say that's a difference of set A and B. Okay, and using our set builder notation, we can say A minus B is, again, using our braces, X bar means the set of all X such that X is an element of A and X is not an element of B. We got to put it and in between there. Okay, so let's look at an example there. Let's say our universal set is A, B, C, D, E, F, G, H, I, J, K. Okay, so the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 letters of the alphabet. A is B, D, E, F, G, H. B is A, B, D, H, I. And C is B, E, G. Okay, and we're going to find these A minus B, or difference between A and B, A minus C, A prime minus B, A complement minus B, or and then A minus C complement. Okay, so the first one we're saying A minus B. So we're looking at the set of elements that are in A but not in set B. So we look at all the A ones and look at the ones that are not in B. Well, little lowercase b is in A, but it's not. But it's also in B, right? D is 1. No, it's not. So the first one we get is E, right? E is in A, but it's not in B. Okay, and then F. Okay, it's not in there. And then G, okay, and then H is in B, so we wouldn't include that. So B, D, and H are in set B, but E, F, and G are not. So we can say A minus B, or the set of elements that are in A but not in B is E, F, G. So that'd be A minus B is just E, F, G. Okay, let's look at A minus C, or difference between A and C. Okay, so we're looking at everything that's in A but not in C. Okay, B, it's in A but it's in C. D is our first one. It's in A, but it's not in C. Okay. E is in C, so we won't include that. So far we're going to use D. Okay. F we would use. G we would not. And H. Okay, so it's just D, F, and H would be those 3. Okay, so that would be the difference between A and C, or A minus C. Okay, so looking for everything that's in A that's not in C. Okay, and that's D, F, and H. Okay, part C, we're looking for the difference of A complement and B. Okay, so we have to find A complement first. So we look at everything on a universal set that's not in A. Okay, so that would be A, C, I, J, and K. Okay, so it's just those 5 elements. Okay, now when we say A prime, or A complement minus B, we're going to look for everything that's in this set that's not in B. Okay, so we start with A. Oh, A is in that set, so we wouldn't include that. C is not in B, so we include C. I is, so we would not include I. J is not, so we include J. And then K is not, so we include K. So just C, J, and K would be A prime minus B. Remember, you always have to find that A complement first. Okay, A minus C complement. Okay, so we have to find C complement first before we do that. So C has B, E, G. So C complement is everything in U that's not that. So we're going to do A, C, D, and then we'll skip the E, F, skip the G, and then H, I, J, K. Okay, so A, C, D, F, H, I, J, K. Okay, now A minus C prime, we're looking for everything in A that's not in C prime. Okay, so B, okay, start with B. B is not in C prime, so we include B. D, nope, D's there, so we don't include it. E, E is not there, so we would include it. F, F is there, so we wouldn't. G, G is not, so we would include it. And then finally H, H is, so we would not include it. So the only ones that are in A that are not in C are B, E, and G. Okay, we're going to talk about Cartesian products now. Cartesian product of set A and set B, and we use A times B, that AXB, or we can read that as A cross B. Okay, it's the set of all possible order pairs of the form A slash B, or comma B, where A is part of A and B is part of B. Okay, so what we're doing is looking at every pairing of elements of each set. Okay, next thing we'll look at is called the Cartesian product. Okay, and when you think of this, think of combinations. Okay, so we select the first element of set A and form an ordered pair with each element of set B. Okay, then we select the second element of set A and form an ordered pair with each element of set B. Okay, so we continue this until you have used each element in set A. So basically, we're trying to pair them off for each possible combination. Okay, so let's look at an example here. Let's say A is orange, banana, apple, 3 fruits, and B is just 1, 2, and we want to look at A cross B. Okay, so we're gonna pair up orange with 1. We're gonna pair up orange with 2. Then we're going to pair up banana with 1 and banana with 2. And then we're going to pair up apple with 1 and apple with 2. So we're looking at all the possible combinations of pairing up elements from set A with elements of set B. And that would be A times B. Okay. So A cross B, we have orange 1, orange 2, banana 1, banana 2, apple 1, apple 2. And then we're listing our ordered pairs. Now we put them in parentheses. And we're saying, okay, here's the element from set A, comma, here's your element from set B. And then we repeat. Okay, another element from set A, same element, and then the next element from set B. Okay, and then we put commas between these ordered pairs. So the parentheses represent an ordered pair, and then we're talking about a set of ordered pairs. So that's why we have the braces on the outside. So here's one ordered pair, here's another one, comma, here's another one, here's another one. So we're talking about a set of ordered pairs. We're going to say A cross B. B cross A, we're going to do the same thing, except we're going to start with elements of B. So we're going to say 1 goes to orange, 1 with orange, then 1 with banana, okay. Then there's a space there, but 1 with apple, okay, and then 2 with orange, and then 2 with banana, and then 2 with apple. Okay, so there's our set of ordered pairs. That's just a typo of the space there, but these are we're going to have the same number of ordered pairs: 1, 2, 3, 4, 5, 6. But we're going to have the numbers first because we're taking B cross A. And by the way, that should not be example 5. That's a typo there, so we'll scratch that type. This is still example 10. Okay, let's look at A cross A. Here we're just crossing elements of A with elements of A. So we're like going orange, orange, orange banana, and orange apple. Okay. So think of this. We could be writing that set A again, right? And then we're going to pair them up from one to the next. So we're going to start with orange, orange, orange banana, orange apple. Okay, so that's how we get the first 3. Okay. And then we go banana, orange, banana, 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 apple. Okay. And then finally apple, orange, apple, banana, apple, apple. So we can, cross a set with itself. And here we get 9 different ordered pairs here. 1, 2, 3, 4, 5, 6, 7, 8, 9. And then finally, we're going to cross B with B. Okay, so I wrote B down again so we can kind of see how we're doing that. But we're doing 1, 1, 1, 2. Okay. and then 2, 1, 2, 2. So this gives us 4 ordered pairs, where we're taking elements from set B crossed with elements from set B.